Hey, good afternoon and welcome. Thank you for joining us for another segment of the Jane Irrigation Training Series. I'm Richard Restuccia, Vice President of Water Management Solutions for Jane, and we have a tremendous program for you today. It's a little bit more technical in nature, which I know I've heard a lot of you wanting a little bit more technical on that side. So today we're going to be talking about a couple things, right? So first and foremost, we want to learn how to best assess an irrigation system, especially on an agricultural site, so on a farm. So this is great for growers, people who are helping growers. So that's really great. We're going to get into distribution uniformity. And really, if you're going to make improvements on your irrigation system, this is a great place to start, probably the only place to start. And this is what's really going to help you learn what you can do to potentially reduce water use, lower labor costs, and increase your yields. So for the first part of it, that's what I'm really excited about. The other thing I'm really excited about is we have Dr. Franklin Gaudi from Cal Poly San Luis Obispo. Go Mustangs.
Yeah.
Dr. Gaudi, he is very well known and well recognized throughout the industry, through academia as a real expert in irrigation. And so we're really fortunate to have him with us today. He's got a ton of certifications. He's a Cal Poly alum. I think it's a dream of a lot of students to think that they can graduate a college and come back and teach there.
Yeah.
He actually did it. I think that's pretty amazing. He's also a certified crop advisor. So he really understands this whole plant-water connection. And then he's also working within the Irrigation Training and Research Center, which has a fabulous reputation around the irrigation industry. I grabbed an old picture of myself when I went through there back in 2000, almost to the date. This was in December of 2000. A couple other people, Joe Loudon from Pierre Landscaping, Travis Bridges from Hunter were in there with me. This thing has legs, right? So you see so many people in the industry are in this industry, and they've learned from the Irrigation Training and Research Center, and they use this for years and years and years, right? This is 20 years that we've been doing this. So anyway, Franklin, welcome. How are things going there at Cal Poly and at the Research Center?
Good. Yeah, because of the current situation that everybody finds themselves in, our professional classes, the ones that we would normally teach, like you are talking about there, we've had to postpone them. We hope that we're going to be able to do it in the summer of 2021, but it's not looking promising now because we're tied to the state requirements here in California, and then the university requirements which follow the state. So last year we weren't able to offer those classes, but I'm hoping that specifically this class we're talking about here, the irrigation system evaluation, will be offered in June. One way or the other. So we have a contractual, some contractual requirements that we need to meet, and then also to, we want to share this information with people that are interested in evaluating irrigation systems. So we're doing what we can. We're doing stuff like this to help as well. So it's going, I guess, is the way to say it.
Well, we're doing it like we're always, especially in the ag industry, we're figuring it out.
Yeah,
right?
That's right.
Just another challenge, and we're figuring it out. And that's what's, it's really commendable about our industry, especially irrigation, that we see that. So, for people who are maybe watching or listening that aren't familiar with the Irrigation Training and Research Center, could you give us a little bit of an overview as to what you guys do there?
Yeah, absolutely. Yeah, the ITRC, the Irrigation Training Research Center, was founded in 1989 by Dr. Charles Burt, and he's an irrigation guru, I guess. He loves irrigation inside and out, all aspects of it. And he started out by working for a dealership, and those dealerships, he felt didn't have quite the tools that were necessary to provide good designs and make good, help growers make good decisions. And so he ended up getting his PhD in engineering, and he focused in water out of Utah State. And then he came back to Cal Poly and he started this program here. And I was a student of the program from 98 to 2003, I guess. And then, you know, I started working for them full time after that, and then I went on. But our center here is intended to provide resources to students. So we are externally funded. Actually, we don't get any funding from Cal Poly. Our funding comes from projects and from grants and from doing work for, you know, the industry. And we take that, you know, we're technically a nonprofit, but we take the money that we do earn and we drive it back into the program here by offering classes, having excellent facilities out in our on campus here for water delivery to irrigation evaluations, you know, and so we are a pillar, I guess, in the BRAE department, which is the Bioresource and Ag Engineering department here, where we are teaching students how to irrigate and irrigate well. And that's really our goal, is to support the teaching program, and then, you know, the other stuff too, like do good things for the world kind of stuff. So that's part of our mission as well.
Yeah, that's great. And you know, the key word that you said there was irrigate well, and
Yeah.
you guys do a really good job on that. So anyway, thank you for helping us understand that. And let's jump into the presentation.
All right. Okay, so while I get this popped up here, I'm going to be covering system evaluations. I've got my presentation here, and just so you know, I've got this set up to actually cover all irrigation methods. I'm going to focus primarily on drip irrigation because I believe that's what a majority of you are here for. But I do want to give you a little bit of background on all the irrigation methods. If you have any questions along the way, feel free to type it into the chat, and I think Richard will read them out for me so I can get your questions answered as we go. All right. So I first want to start with what is distribution uniformity, because that's ultimately what a system evaluation you know, is conducted for, is to determine what the distribution uniformity is, or DU. You know, those of you that are hunters, you might think of Ducks Unlimited or something here, but in this particular section, we're going to be talking about distribution uniformity. So the definition is a measure of how evenly water is applied to the field. Sounds really simple, right? It's actually a little bit harder to do than you might imagine. And one thing that people get confused about is how we describe the units of distribution uniformity. They often want to call it express it as a percentage. And then everybody gets confused with efficiency. And so I'm going to show you efficiency here too in just a moment. But so we personally, and the IA, the Irrigation Association, has adopted using the decimal form of uniformity. So you'll see me saying there, like the DU is a 0.9, right? And for center pivots and linear moves, that's very achievable. For drip, you can actually get quite higher than that. You can get 0.95 if you're really doing a good job. Surface irrigation, you know, probably going to be in the 0.8 range. But we can compare all these systems across the board using this term distribution uniformity, and that's really what we're trying to do. So, and remember there that a DU value of 1.0 would be perfect. Okay. So just a little graphic for you here. This is what distribution uniformity looks like. You can see the bottom one there is would be a good distribution uniformity, where all those plants get essentially an equal amount of water. Whereas the graphic on the top there shows you that the plants, some of those plants are not getting the same amount of water. And then to contrast that here, so here's where I'm talking about right here. I got to turn on my pen here. I have the ability to write on the screen if I can. Actually, maybe I don't oh, there it goes. Okay, so there's your, your spot where you're under irrigating. And you, in the end, you applied the same depth of water here on both of these, right? But some of our water end up being, applied in a spot where it wasn't needed. And so we want to have the bottom graphic there where we're applying the same amount of water at both locations, or all locations in the field. Okay? And of course, it's never going to be perfect, but we want to get it as good as we can. So how do we calculate it? Just real quickly, here's the equation. We use the average of the low quarter compared to the average depth infiltrated across the entire field. So you can see, again, I got a pivot in the background just as an example. If looking at that picture, you can see, wow, that field looks really uniform, right? And so how would you know where the lower spots in the field are whenever it looks that good? Well, you have to evaluate it, right? And so we would put buckets, as rudimentary as that sounds, we put buckets out underneath that machine. We let that machine run over the buckets, and then we determine, are all the buckets getting the same depth of water or not? And then you can find the buckets, a quarter of the buckets that have the low values, average those up, and then average it with all of the buckets, and that would give us then our distribution uniformity. That's a very simplistic way of looking at it for this particular machine here. Okay, so why do we worry about a good DU? Well, there's several benefits to having that good DU. Of course, the first one is that we do want to increase efficiency, and I think this is often where the confusion comes in, because in order to get really a high efficiency, you also need to have a good distribution uniformity, right? Now, it is possible actually to have a poor uniformity and get a high efficiency, and that is by under irrigating heavily. Okay. But in this case, we're assuming that we have good scheduling. We're trying to minimize deep percolation. So the way you get that good efficiency is by starting with a good distribution uniformity. And then it also simplifies our irrigation scheduling. The more uniformly we can apply the water, the easier it is to make estimates of how much we need to apply and when we need to apply it, because the whole field is basically growing uniformly rather than having spots that are hit and miss, so to speak. It also does increase the representative sampling in the fields. So if you're taking soil samples, right, you pull some soil samples. This picture on the side here is obviously pistachio field with a drip line in it. It's actually an organic one, and we were doing an evaluation there. And so if you're taking soil samples, right, and you're applying different amounts of water at different spots in the field, well, if you're fertigating, you're going to end up with different fertilizers at different spots in the field. And so that's a challenge as well. So you want to apply the fertilizers uniform, and if you're injecting the fertilizers in the water, well, then you have to have a good distribution uniformity. So soil sampling ends up being better, plant sampling ends up being better. And then also the last one here is it also, if you're using soil sensors, right, how do you know where to put those soil sensors? Well, if you have a level playing field, meaning your uniformity is good, all the tree growth is good and everything, well, then putting the soil sensors in maybe is a lot easier because you might be representative. But if you're not applying the water uniformly and your tree growth is different or your plant growth, whatever it is, then putting in soil sensors maybe doesn't help at all, because you're just monitoring a spot that's either doing well or a spot that's doing poor or something, right? So it's a little bit challenging. So just to give you maybe a little bit better perspective on that, this was an example of an evaluation. This was actually a pivot. Doesn't matter though. Just the concept is the same. But we put buckets under the pivot. We let the water go around, and you can see the blue line there, right, is how the water landed in the buckets. Ultimately, we would hope that blue line was a nice, perfect straight line, right? We did the evaluation, and you can see at the top up there, the distribution uniformity was a 0.73. Not terrible, but not great either. So we went through the entire pivot package, fixed all the sprinklers, made sure it was as designed. We reevaluated it. You'll notice that the red line now is the new evaluation. It is not perfect, but it is definitely better. A lot fewer highs and lows. And you can see now it's basically performing at the design there of 0.9, which is right about where we want to be. Okay. So what does this mean, right? Obviously, the number means something. 0.9 is better than 0.73. But let's put it into perspective in regard to the soil sensors that we were just talking about. If we were to say, okay, how well did the first evaluation, how uniformly was it applying the water? Let's just say we're shooting for a representative depth, right? An average depth. And so that's the 1.0 there, okay? And so how many values from this chart here, how many of those blue dots there are within plus or minus 10% of that mean depth that we were trying to apply? And based on this data that I had collected, you could see it was about 36% of the values were actually within plus or minus 10% of the average depth. And so you might think to yourself, well, really, that's only a third of the field, right? That means that a third of the field is getting more water, and a third of the field over here is getting less water. So thinking about where you place your soil moisture sensors, again, if you have this distribution here from uniformity here of 0.73, you have basically a 36% chance that you install it in a quote unquote representative location in the field. So what happens then whenever we improve that to the 0.89, right? So now our distribution uniformity is much better. And now we have essentially a 71% chance. Almost 3/4 of the field now is going to be getting within plus or minus 10% of the, the target value that we were trying to apply. You'll notice the wettest spot in the field now is quite a bit lower than it was before. And the driest spot in the field is also closer than before. Okay, so distribution uniformity obviously is going to be very important. And so now the question becomes, well, how do we evaluate it, right? And that's what I want to get into here a little bit. But before we do that, let's just talk a little bit about efficiency.
Can I ask, we got a couple questions. All right, if we ask them right now?
Yeah, absolutely.
So one of the things you said is you want to avoid deep percolation. Why do we want to avoid that?
So deep percolation, it depends on how you look at deep percolation. Deep percolation can be a beneficial use if we're leaching salts, right? And so that would be an intended deep percolation. Deep percolation is when water moves below the root zone. And if water's moving below the root zone and it's not being used, that means it's just going to go into the ground. And so water that you paid for, you applied, is now past the root zone and won't be used again. Now, with that said, though, what a lot of people are figuring out these days is that as we improve efficiencies or uniformities on farm, we also don't recharge the groundwater nearly as much, right? Because what ultimately happens to that deep percolation is it ultimately ends up back down in the groundwater. So as we become more efficient, we also are probably depleting some of our aquifers more now because some of that water is not making it back. So deep percolation, yeah, we don't want to have that unless it's intentional. Groundwater recharge would be an intentional use, or leaching of salts might be intentional as well. Yeah. And you had another question?
Yeah, thank you. So, and then I know you do some work in landscape irrigation too. Mm-hmm. We're hearing distribution uniformity numbers, right, of 80, 90, 95. What are they typically in landscape applications?
Yeah, great question. Typically, if you're in the 0.7 range, you're doing excellent for landscape. It's just the technology. Don't get me wrong, technology is still good. Often it's sprinklers, though. It's not drip. Drip can be higher for landscape if you're doing subsurface drip or something. But yeah, with the spray heads and the wind patterns and and so forth, yeah, often a lot of audits of landscapes will show that you're in the 0.5, 0.6 range. And not the 0.8, 0.9 range like we hope to be with, with our ag systems. Now you might say, well, why don't they improve it, right? And honestly, there are a lot of folks trying to improve it, but the problem is that you can get a lot more bang for your buck in a 100-acre ag field than you can on a 2,000 square foot lawn. So there is a lot of people trying to improve that area, absolutely. Yeah. So the IA offers a CLIA exam or a CLIA certification, and it's all based on stuff that the ITRC also developed and gave to them. So it's essentially the same idea that we're talking about here, is evaluating a system.
Yeah. All right. Great. Thank you.
Okay. So the question here is DU different than efficiency? And I've been explaining that a little bit. Absolutely, yes, it is, right? Efficiency describes how much water is beneficially used compared to the amount of water applied. Remember, uniformity is how evenly we apply the water. Efficiency is now talking about of the water we applied, what of it actually went to the crop. So in this particular photo here, I intentionally picked this photo because it's a drip system, right? And water never runs out of drip field, okay? And so the drip system may actually be applying the water with a high uniformity, but now efficiency is low because now it's a management issue, right? Running the system for too long, the soils can't absorb the water that is being applied. And so now the water runs out of the field. So you can have a very high efficiency here, but now have a high uniformity, but now have a relatively low efficiency because we are not using all that water. This one, again, is expressed as a percentage here, right? And that's, again, we keep DU as a decimal. efficiency as a percentage. So that way, whenever I say 90%, you know what I'm talking about, right? And the industry is still somewhat struggling with this a little bit. A lot of people are on board, but yeah, there is a distinction there, and it can be, it can be hard to decipher sometimes. So often I'll ask, are you referring to distribution uniformity or efficiency when they tell me a number? Okay. So here's kind of a key piece, right? It's the percentage of the applied water that was beneficially used. And that, again, the key word there, percentage. And so what is a beneficial use, right? That's the kind of the guts of it here. And that's what we need to understand. And this, of course, gets a little bit loose depending on who you talk to, right? So I have a slide here on what is beneficially used, but just so you know the equation, this is it, right? Efficiency is water beneficially used compared to the total applied. Whereas remember with uniformity, it was the average of the low quarter compared to the average of all. So that's different, right? Definitely different. So here's an example of efficiency. Looking at this chart, you might say in both cases, the distribution uniformity is good, right? We don't have really a low spot or an under irrigated spot. What we have instead is you have the right amount, meaning we shut the water off when we refilled the root zone. And in this case, you can see it probably ran for almost twice as long as it needed to. In both cases, again, the amount of water is basically flat, right? It is a really high distribution uniformity, but we let it run for too long. So understanding, again, the difference between efficiency and uniformity is a kind of a key piece there. And of course, when we do evaluations, we're focused more on, are we applying the water uniformly? Because we have to get that down before we can get to the efficiency piece. All right. So in this case, you could say maybe this is, 95% efficient. Most all of the water is going to go to the plant. Where in this case, it's maybe closer to 50% efficient because half of that water there is depercolated, going below the root zone. Now, again, is it going to the groundwater? Was that actually, we don't really consider that. We applied the water for the purpose of growing the plant. And so that's what we base the efficiency on. Okay. So here are some beneficial uses. Obviously, crop ET is the biggest one, right? We want to produce food and fiber. So that's the biggest one there. Leaching salts, and in some cases, in some areas, especially here in California, we have some salt problems. And so that's a big one. Crop cover, if you're in the grape industry, maybe, you might have some crop covers also in trees, they have them as well. Climate control, if you're up in Washington, I don't know where everybody's at, right? So I'm just kind of throwing out some ideas here, but you're up in Washington, maybe cooling of apples, right, would be an example of climate control. Frost protection, again, is also an example. And then weed germination. You might think, well, why is growing weeds beneficial? My students always ask me that. And I said, well, it's not actually that we're growing the weed. What we're doing is we're germinating the weeds so we can disc it under. So that way, when we plant our crop, there is no weeds in our crop. So that's really the beneficial use there. So this is just a photo here of some potted plants, blueberries, I believe it was. And this is, we want pretty much all that water to be applied to go to that plant, because these have holes in the bottom, right? And so you might even be able to see that there was probably some leaching that comes out of these pots here that's leaking out, right? And so we're not 100% efficient, even though they are really trying to be, right? Every once in a while, you just apply a little bit more water than the plant can take up or the soil can hold. And in this case, it's really hard because it's not even soil. It's a substrate, which is artificial soil, which has very minimal holding capacity, water holding capacity. Okay. So irrigation managers, those of you that are in the field actually doing irrigation scheduling, so forth, should prefer DU over efficiency. And the big reason why is because DU is repeatable. We can make that system work well, right? It's kind of like you can fix your car and know that it's working and it's going to do a good job. It can be maintained. Whereas efficiency is a little bit different, right? We don't know how well we did until after the season's over or after the irrigation event's over. Just like you don't know how well your car is going to get in terms of fuel mileage until after you drive it somewhere. You have an idea of what your fuel economy might be when you drive from here to somewhere else, right? But you don't really know until you hit traffic, until you hit a headwind or have the wind blowing behind you or whatever it is, right? So we know that our car is going to function at a high, distribution uniformity, so to speak, right? It's going to be well maintained, but then how you manage it is what drives efficiency. And so
Dr. Gaudi, so we know that we can measure DU with a catch can test or bucket test, as you mentioned. Efficiency, we know the formula to get there, but how do you measure efficiency?
So you measure efficiency by knowing the amount, and this is where I was saying it's a little bit subjective. It's the percent or the water beneficially used compared to the total applied. Of course, knowing the total applied is pretty easy, right? Because you can just look at a flow meter and get an idea of the total applied. But now, how much of it actually got taken up by the plant, right? And this is where we'll all argue over it. This is where we use NDVI images. This is where we use programs like Metric to use satellite-based or high-resolution images to make estimates of how much of it actually went to the plant. And so, yeah, again, it's not the easy one to do, and that's why a lot of people prefer DU, because at least we know we're applying it uniformly.
Yeah.
All right, so now let's get into the system evaluations. I'm going to start first with surface, which I know everybody loves, but I still cover it because, around the world, it's still a very large percentage of irrigated land. In California in particular, it's still 45% of irrigated agriculture here. So surface irrigation, here are the factors that affect distribution uniformity of surface irrigation. All right, you can boil it down to basically two things. Two components of uniformity. The first is opportunity time differences. That means essentially how long does this soil at this spot in the field have to soak up water compared to this soil at this spot in the field, right? So that's one of them. And then the other is infiltration rate differences. Okay, so how fast can the water go in over here versus how fast can it go in over here? And of course, there's factors in each of those components. So under the opportunity time differences there, you have things that a lot of them of which you can control, right? How fast you put the water on, for example, how long you put the water on. What is the length of the border or furrow? Land grading, again, soil roughness, meaning is there a lot of vegetation on the surface or is it bare soil? And then flow restrictions, is the soil got, maybe some high spots in it or something that's slowing it down in this side of the field versus that side of the field. You'll notice most of these opportunity time differences you can control, right? You have the ability to fix. When it comes to infiltration rate differences, you'll notice some of this we can't control now, right? The soil texture and structure. If you have sandy spot in one part of the field and clay in another part of the field, that's kind of hard to fix, right? It's doable, but that means probably lots of dollars. So, you're kind of stuck with that. So obviously you might want to break that section up, right? Here's one way of fixing that is you break out the sandier spots compared to the clay spots and you irrigate them differently. Okay. Wetted area, if you have a furrow that's maybe, the actual furrow, not the beds, but the furrow that's maybe a foot wide here and the other one's 18 inches wide, you end up with a bigger wetted area in one versus the other. And so that sometimes will happen on what I think they call them the skip row or whatever, where basically the tractor makes a pass of, let's just say 10 furrows, right? And then it turns around, it comes back and it makes another pass. Well, there's that row in between the 10 going this way and 10 going that way that sometimes isn't always the exact width as the other ones. And so that would be an example there of different wetted areas as you're flooding down. Soil compaction. You drive tractors down certain rows and not down other rows. And so the water's going to infiltrate at different rates in a compacted furrow versus non. Salt issues, right? Even the difference, this is very minimal now, but even the difference in viscosity of water due to temperature from day sets versus night sets actually impacts how much goes in. Okay, so that's surface. Let's talk about sprinkler real quickly. Okay, so with our sprinklers here, we have, we've got 4 components now that you can boil it down to, and the difference between the flow rates of the sprinklers, how well the sprinklers apply the water as it flies through the air and lands on the ground, that's the catch can uniformity. Unequal drainage, so sometimes when you start up, it takes a while for the water to make it all the way to the end and actually shoot out the last sprinkler. And then on the other hand, when you turn it off, maybe that last sprinkler's downhill, and so it continues to irrigate for a little bit after you shut the water off. And then edge effect. We have to have overlap between sprinklers to get to get good uniformity. And at the edge of the field, you don't get that overlap. So you can see a lot of the, again, the factors that affect these things. Of course, pressure differences affect flow rates, right? Elevation changes. That's the same is absolutely true for drip emitters as well. Wear, nozzle wear, plugging, you know, all that stuff. And then the catch can, the spacing is the big one. And when I say spacing, this is how far apart they'll put the laterals. If you put the laterals too far apart, you don't get as much overlap. And when you don't get as much overlap, your distribution uniformity goes down. Okay. But of course, people spread out those laterals because of labor cost, right? You have to move those pipe, especially with hand move or side roll or something. So there's a cost associated with that. So I'm not going to go through everything here. You can kind of see it there. But bottom line is we've done a lot of evaluations, and you can see that catch can DU, which are highlighted in blue, those are things that would affect the catch can DU, or 60% of the problem often. And then the ones that are highlighted red there are GPM DU. So of the 4 components, you can see that almost 95% of the problem is because of either catch can DU or GPM DU. So in other words, focus on getting your flow rates as uniformly as possible out of all the sprinklers, except for center pivots, those are an odd one. And then also focus on trying to make sure that as the water flies through the air and lands on the ground, that it's doing that as uniformly as possible. Okay. Of course, I just explained this, the fixed grid sprinklers, you know, like the solid set, the hand move, the side roll, the 2 major factors, of course, are the catch can DU or the overlap DU. And wind, of course, is a big player in that one too. I should have pointed that out. And then the flow rates. So this is some evaluations we've done, you know, determining the flow rates from the sprinklers, measuring pressures, you know, and then also doing overlap, determining how well the water flies through the field there and lands in the bucket, or flies through the air and lands in the buckets. So you take all this information and then you can compute what the uniformity is. Okay. So let's get into drip micro, which I think is what most of you are here for. And I want to make sure that I can get through as much of this as I can before we run out of time here. So the quick note about drip is, you know, with sprinklers and surface, we're often trying to wet 100% of the field area, right? And so we can put out buckets and we can measure how the water lands at all these different spots in the field. But when we're talking about tree crops and row crops, often we don't care if water gets right here, right? We don't need water there. We need the water where the plant roots are at. And so the evaluation is a little bit different in that we don't look at, you know, things like catch can DU. We focus more on, you know, is each of these emitters down here, right, emitting the same amount of water in the root zone of those plants. Okay. So here's the factors that affect drip and micro. Changes in pressure is obviously a big one. And then, you know, you can see the factors that affect that, same as before: friction, elevation changes. One other one here that I added is pressure regulators. Often they'll put pressure regulators at the head of a block or the head of a hose. And especially if they're adjustable. If they're the adjustable ones, sometimes they don't get adjusted correctly. You can see that a whole block is 5 PSI lower than all the rest of the field, just simply because the pressure regulator wasn't adjusted properly. And that has an impact, obviously, on if the whole field is getting the same depth. And then backflushing too. Sometimes people forget that when the system goes into a backflush, it starves the drip out there of some pressure, because it's taking energy to make those filters backflush. So if you have filters that are constantly backflushing because of water quality is poor or something, then you might not realize that that's actually having a big impact on your uniformity as well. Flow differences caused by other factors. So we linked a bunch of stuff together and we call it other factors, because it would turn into a thesis for a grad student to do an evaluation in a field if we didn't group them all together. You know, these evaluations, we want to be done in a day. We want to go through a field, actually maybe even faster than that, 6 hours or something, right? Go through a field and figure out what's going on and make recommendations to improve it. And so we group things together in order to kind of keep it, manageable. So CV there is a big one, right? Richard knows all about that one, because Jane focuses a lot of energy on making sure that the coefficient of variation between every emitters is very minimal. They want every single emitter to do exactly the same thing. And of course, it's hard for them to do that because it's 110 during the day when they're manufacturing, and it's 85 at night when they're manufacturing. And so making the process perfect is not always going to, it's not really realistic, to be honest. So, but they do a very good job of trying to minimize differences because of the manufacturing process. Insects, you got all kinds of different things that chew on tape, that eat through hoses, right? I mean, all that is a problem. It leads to non-uniformity. Plugging, of course, is a big one, right? If you don't have proper filtration. Where you wear out the tortuous path, and so it gets a little smoother, so then it changes the characteristics of the flow rate coming out of it. All of those things impact ultimately the distribution uniformity. And then we have unequal drainage down there and unequal spacing. Unequal spacing is like, I added on 10 acres to this field, and I planted it, instead of being planted at 18 by 20, I planted it at 18 by 19. Now all of a sudden, and I kept the same number of emitters per tree, right? Now all of a sudden, I end up with more emitters in a given area because the tree spacing's tighter. Well, now you're applying more water in that area compared to the rest of the field, right? And so there are fields out there like that, don't get me wrong. People add on and they change the spacing, but that's a little more uncommon. And then the unequal drainage, pulsing is a big problem here, right? And like on that potted plant one I showed you, the substrate, they have to basically turn it on and turn it off. So they're on for 5 minutes, off for 30 minutes, on for 5 minutes, off for 30 minutes. And every time they do that, you could have some non-uniformity due to drainage. Now, of course, manufacturers like Jane have special check valves in their emitters and stuff to try to prevent that. But all it takes is for one of them not to do quite what it's supposed to do, and then unequal drainage is a problem, right? So this is some recent data from 2016 to 2019. I sent teams out into the field, and this is for drip systems and micro systems. These are some of the data points here. You can see with drip systems, the other reasons, primarily plugging, is the main problem why we don't have perfect uniformity. Whereas when you get to drip and micro, it's more about pressure differences, right? And the reason why on that is because often with micro sprinklers, the emitter hole, right, the path that the water flows through is bigger. So plugging doesn't tend to be as much of a problem as it does on the smaller emitters. And then on top of that, often too, these are not PC as often as the emitters are. Typically, the emitters, a lot of emitters now, almost everybody's making PC emitters. You can get non-PC, but you almost have to ask for them these days. Whereas in the micro world, you can still get a lot of sprinklers that are non-PC. And so when it's pressure compensating, right, pressure differences actually don't tend to be as big of a deal anymore because the emitter does a good job of making the designer look good. You could actually be a pretty terrible designer and still have a uniform system out there if you pick a good PC emitter. So I hate to say that out loud, but there's some truth in that. So looking at the drip and micro, you can see the average values over those years there. Drip is about 0.85 and micro is about 0.82. So, and what you'll see here on this chart is that these are over, almost 2.5 decades now, I guess, right? What you can see here is that drip is kind of on this upward trend, as is micro. We have some odd years in there because we went to, an area like along the coast where they need some help and they haven't been getting maybe as much help. And so you have a low year in there or something because of that. But if you look there at the trend lines, the straight lines that are kind of at an angle, both of them are on an uphill trend based on all the data we've been collecting over the years, which is good, right? And that's partly too because technology from the manufacturers is getting better, designers are getting better, right? And we like to take credit for all of it, but it's not, So, but the idea is it's getting better, and that's what we want to see. So let's go through the evaluation procedure here real quickly. When you evaluate a system, in this particular case, there's actually 4 manifolds. It only looks like 2, but right here at this connection here, sorry, it's red, I know, and here, we actually assume that one manifold goes in this direction, and then the other manifolds go in this direction. So we actually would consider this to be 4 manifolds as we're evaluating it, not just 2 manifolds. Okay. And so then we have to take pressures systematically across the field. We typically go closest to the head of the manifold and then the end of the manifold. And then we go closest to the manifold here and then the end of the manifold down here. And so we systematically go across the field knowing that the pressure difference as you move in this direction, right, is going to be the greatest. And you can see here it's 21 PSI and here it's 16 PSI. And that's because of friction and elevation change. And so we want to see what are the maximum variations that we have in pressures across the field, because that tells us then, you know, how uniform the system might be because of pressures, right? And then we need to pick some locations to evaluate. We will always evaluate the emitters for the other causes. And so we often will pick the A location will be closest to the pump, basically a clean location. The B will be somewhere out in the middle. It could be really anywhere in here, right? This happens to be where we pick to do it on this one. And then C happens to be the dirtiest location, the end of the line, way down at the end of the manifold where dirt and stuff will collect in the system, and we'll evaluate that there, okay? And then I have D on here too. This is really because it was a PC field and we're trying to make sure that we get good data for how well it's performing here. So let's take a look at an example here. How much time do I have? I got a few minutes still.
Yeah, plenty. You're doing great, Frank.
Okay.
Thank you.
And we're good on questions at the moment?
Yeah, right now we're good.
All right. So let's take a look at an example then. So first thing we would typically do with an example, or when we do an evaluation, is we'll do some inspection, right? Do they have a flow meter? Because if they don't have a flow meter, we like to say around here, if you can't measure it, you can't manage it, right? So you have to have a flow meter. So, you know, first thing you should find is a flow meter. If you don't have a flow meter, that's number one recommendation. Put in a flow meter. Because otherwise, how in the world do you know what you're doing, right? Yeah, it's really hard. If you imagine trying to drive without a gas gauge, right? It can kind of do it, but you just never really know. And then we look for things like this too. We want that valve to be completely open. We don't want to throttle valves, because if we're throttling valves, it means we're burning energy, which is basically flushing money down the toilet. We don't want that. So we will go through the filter station and we'll identify, things that maybe they can improve there, like are valves open? How often are they flushing? The back flush happening. Do they have flow measurement? Right? All these questions, by the way, are outlined. The questions you should be asking and looking for are outlined in our program, okay? Which we have available. It's part of a book that we sell, so you get the software in the book. Okay. Then we go through the field systematically taking pressures. Ultimately, you would want to see the same pressure everywhere, right? And in this particular case, you can see we're seeing pressures up there at 18 psi and as low as 6 psi. This happens to actually be a field that had Jane product in it, and it was the Jane top drip. And Richard, pop quiz. What's the minimum pressure requirement on the Jane top drip?
I'm going to take a wild guess here and say 9.
It's actually 6, yeah. And so in this particular case, they're right on the edge there of making sure that they have the the right pressure available for this particular emitter. Okay, so here's the emitter. This is actually the hardest part of an evaluation. If you're evaluating your own field or something, you probably know what's out in the field, but I send out teams of students and we go through these fields and we have no idea what they have out there. And you know what my favorite line is? What do you have out in the field? Netafim. And then you go out there and you're like, actually, that's Jane or whoever else. They just like throw out the first word that comes to mind in terms of manufacturer or something. And so you gotta know what's out there. And so in this particular case, there's your Jane top drip, and you always know if it's PC. So they cut apart the emitter. That's one of the things we do as part of the evaluation. You cut it apart. You look here in the emitter, you look for plugging, you look for what's in there. Is it sediment? Is it organic? Corey Broad.
Yeah.
Corey, he did a nice thing, I guess one of these seminars on flushing and looking at the emitters and so forth. So you check that one out as well, because he covers some of this stuff in better detail. But then once you kind of know what you're looking at, often the manufacturer will have some data that you can pull in here. And so you need to know, what is the exponent? What is the minimum pressure there? There it is. Richard, you were so close, right? Minimum pressure is actually 6, maximum 44, right? And then you notice which flow rate is it here? Is it a 0.53 or 0.61, right? Or is it a 0.42? So you have to figure this stuff out. It's not as easy as it sounds, right? And that's kind of a problem. Really good growers, they absolutely know what they have. Some growers, they'll be like, well, I just bought this field. I have no idea what's out there, so good luck, right? So then you go through and you do your evaluation, you know, monitoring how much water is coming out of the emitters at those 3 locations we were talking about, the A, the B, and the C, the clean, the average, and the dirty locations. And then you take that data and you plug it into our program. Next, you want to go through and you want to do a, you want to do a little simple flush of the hose. And this is my favorite. How often do you flush hoses? Oh, we do it like once a week. And then you go over there and you flush the hose and this is what comes out of it, right? Yeah, absolutely. You're flushing it once a week, right? But it's the manufacturer's fault that it's not giving me a better uniformity. Okay. So I'm not picking on anybody or anything, but I've just seen this a lot, right? Where it sure, seems like, man, there's a problem out there and we can't identify what it is. And that's part of the evaluation, is identifying those problems. So if you don't mind, I'm gonna go ahead and I'm gonna pull up here an example of the evaluation program and just walk you through this here. So we've got this Excel spreadsheet. Again, it's part of our evaluation software. If you want to get it, you can get it from the ITRC.org website. Okay. And so I thought I made this in any case. Yeah. So here we go. So it starts out by first just give us some identification of what it is, what's the crop, where is it located, right? And then you now start to ask some questions about the system. Okay. So how old is it? Do you have problems with penetration? How many different types of emitters are out there? And they always say 1, and then you go out there and you do a little looking around and you realize they have online emitters and inline emitters all in the same field, right? So here's an example, with the Jane top drip there. You have to identify which nominal flow rate it is, if it's pressure compensating or not, right? I'm not going to go through this whole thing, but you can see we have all these questions. And we also have a whole ton of documentation here that goes with it. Field data sheets that allows you to print them out and just put it on a clipboard and collect all this data while you're in the field so you can bring it back, right? And plug in all this data. We go through the filtration, the chemigation systems, pressure measurements at the pump, right? What kind of valves do you have out there? Right. Then we go through and we collect all those pressure measurements that we were just talking about, right? At those systematic locations in the field, we plug all that in. Then the program does all the magic for you, okay? And then you continue on down here, and do you have hose screens in your field? This is a big one, right? A hose screen, often people put a hose screen at the very beginning of the hose to keep the emitters from plugging up, but then it plugs up the hose screen and plugs up the entire hose, right? So we want to check if they have hose screens. Often a recommendation is to remove those. Then you go through and we do those locations, measuring all of the flows from all the emitters. And you can see here, looking at these emitter flow rates, right? They're very, very similar. That's good. We note what the pressure is and what the collection time is, right? And we continue to do all that. And then one of the nice things that I have in this program now is now it will automatically populate a graph for you. So based on the data you can collect here and the input data, here is where based on what Jane says it is in the manufacturer, right? It's supposed to be 0.53 and it engages at 6 PSI. And so based on the data points we collected here, here's how well it's performing. Okay. Now, with that said, it doesn't look perfect, right? And to be quite honest, none of them do. But this is also an in-field actual evaluation, right? It's not right off the line manufacturer perfect, everything is ideal. This is, by the way, all that sediment that you saw on the hands, that was from these emitters. So these emitters are still doing a pretty decent job, even with those, that sediment and stuff out there. So we ultimately end up populating this chart, and then we also knock out the results here. So here's the ultimate DU of this field, 0.91, really, really respectable, right? And then it also then breaks down why is it not better, right? The reason why it's not better largely is because there are some pressure variations in the field. You saw the 2 pressure gauges I showed you. That was from this field. The one was at 18 and the other one was at 6, right? So we're seeing big pressure differences in the field. That's largely the reason why this isn't better. Now, of course, that 0.91 is really pretty good already, right? But it could be higher. And then, you know, other reasons like plugging and so forth, 16%. And then it also gives you an idea here of, you know, what you could do to improve it, right? Based on the data you input, it's pointing you in some directions. Here's some things to think about and look at. It's not saying this is absolute, but it's giving you some ideas, right? Look at one of the options here. Line number 40 says, maybe you should do some more frequent back flushing, right? And obviously based on the pictures you saw, that's would be a very good thing to do. And then last thing I'll show you here is this. It also knocks out some basic irrigation scheduling based on your evaluation. We ask the grower, how long do you run for, right? And they say, I run for 3.4 hours a day. They actually tell us on a weekly basis. We're computing it to a daily basis, but we're saying that we think you should be running for 4.5 and you're running for 3.4. So you may be under irrigating slightly, right? And then we give them some graphics here too, like in your area, right? Then we have an error bar on here basically to say, hey, you know, it's not perfect. We're using estimated ET values and your estimated run times and all this other stuff. So in reality, you might be pretty close to being right on, right? Maybe you could use a touch more water. And then looking at this, sorry about it being kind of glitchy. I think it's because we're going through Zoom here, but this max set duration that we estimate based on your soil type and so forth is only 31 hours and you're running 24. So that's good because you're not going to have deep percolation doing that, right? But however, you look at how often you irrigate, we're saying you should only have 163 hours between irrigation events and you're doing 168, which could be leading again to under irrigation potentially, right? And so we have this stuff all built in. You plug in, you fill out the form, and all of this stuff gets generated for you as part of the program. So, and then in the end, ultimately what I'll do, and this is an example here of a report that I pieced together for this particular grower, utilizing the information that we got here. I told them what the DU was, and then, you know, just the field DU is good, right? But here are some reasons why it's not perfect. And then, you know, a considerable amount of sediment was flushed, so you should probably consider flushing more often. And then those things always pop up at the best time, you know, it's never. And then, you know, fertilizer injection, we noticed too that they were injecting downstream of the filters. That's kind of a problem because if anything precipitates out from what is injected with the water, it's going to plug up your emitters rather than plugging up your filters. So, you know, there's a lot to learn here. Obviously, I kind of skimmed through it here in 50 minutes, but that's the goal, right? Is to ultimately know how uniformly we're applying the water. Don't confuse it with efficiency. And then how do we make some good improvements now to, or good recommendations for improvement?
Yeah, so a couple things here. First of all, what an amazing report and evaluation. And this is quite impressive. Now, do you guys do this as a service for a fee? Or do you teach people how to do it for themselves?
Yeah, so great question. Both. Typically, the Department of Water Resources or the U.S. Bureau of Reclamation, they give us contracts. We're a little nervous about both of those contracts going forward because of COVID, you know. But from, as you saw there, 1992, I believe it was, all the way through 2019, this service has been provided for free to growers that were interested. Okay. And so they would fund it. But we've also had large growers come to us and say, will you guys do evaluations for us? And the answer is yes. You know, obviously, if we do a single evaluation, the cost is a lot more than if we do a lot of evaluations. So typically I need to put a team together. It's usually 2 students. I have to have a vehicle for them, all the equipment for them. And so usually if we're doing that, I want to do 40 evaluations for the team, and it ends up being somewhere around $1,200 per field, yeah, which sounds like a lot of money, but you divide that out by the acreage, it's really not that big of a deal. There are other, you know, RCDs and so forth that do these evaluations, and most of them have been trained in our classes here that we offer typically on an annual basis in June. And again, I'm trying to make sure that that happens this June. You might be able to take that class if you're interested.
Yeah. And then so the evaluation software, is that free or does somebody have to pay for that, or can you even buy
So
it?
when you attend the class, you get it for free as part of the class. But if you wanted to get that software, we have a book. I'm going off the top of my head. I think it's $100 book. That is the evaluation book, and it comes with the software. And so you can order we call it the ISE Irrigation System Evaluation Manual, and it would come with that software that I was just showing you if you wanted to do those evaluations. Yeah.
Okay. And then how many different crops are part of that, right?
Yeah. So really, I don't care what the crop is, right? That particular evaluation software that I was showing you is for drip and micro only, which is what 95% of the people want to evaluate. And so you can do actually under tree sprinklers with it. The process is very similar to, what's the difference between a micro sprayer and a under tree sprinkler? Really, they're the same thing, right? One's just a little bit bigger flow rate nozzle. So you can use this program also for under tree sprinklers. So it works on vegetables. It works on, trees. It works on vines. It even works with subsurface. If you want to take the time to dig it up and do the evaluation, you can still do it. Yeah.
Yeah.
So it doesn't matter what the crop is. And by the way, in the program, in the documentation, it says, what are you doing? And we have graphics that will automatically change to help you determine where and what you need to do. If you're telling us it's trees or if you're telling us it's a row crop, we'll change graphics and stuff to try to make it as easy as possible.
Yeah, fabulous. A couple more questions here.
Absolutely.
One very specific, and this goes back to sprinklers. Say we have a block of 20 rows, 400 trees, 400 sprinklers. What would you recommend for a catch can setup? So again, that's 400 trees.
So under tree sprinklers, I'm guessing is what they're referring to. And so if it's under tree sprinklers, because I mean, they said trees specifically, right?
Yeah.
So you actually don't need to do a catch can test. We don't really care, like in that picture behind you right there, right? We don't really care that the area between those trees actually gets wet. What we care about is that each tree gets the same amount of water. So you don't need to do a catch can test on that. What we would do is verify that the flow rate of all of the sprinklers in the field are uniform. Because if they're uniform, then that means the trees are getting basically the same amount of water. So yeah, we don't need to do a catch can test actually on that.
Okay, great. Then the last question here is when doing a catch can test on drip, do you have to go all the way down the road? Do you just do sections? How far down the row if you're starting away do you start?
Excellent question. Yeah, and of course there's lots of details I didn't get to cover here in this time frame, right? This is actually a 1-week course. If you were to take it at Cal Poly, we spend 2.5 days in the classroom and then 2.5 days out in the field doing these evaluations. So to answer the question though, what we want to do is at each of those 3 locations, the A, the B, and the C, we want to test 16 emitters at A and B and 28 at C. You might say, well, why are you testing more at C? Because that's the dirty spot, right? That's the spot where we're probably going to find all these other reasons. And when we test those, we want to test them at the exact same pressure or within a half a PSI, because we're trying to test all the other reasons other than pressure differences that there's a problem. And so we typically will get 28 emitters as close as possible. So that way friction and elevation changes and so forth aren't an issue. And so you test those in a group, making sure that so we will poke a pressure gauge in at the first emitter that we plan on testing, the last emitter that we plan on testing, and making sure that we're getting the same pressure there. Then we'll run the test. Because if we have 10 PSI where the pressure difference between those emitters, then we're not testing the other reasons. We're actually testing the pressure things, which you've already done with the systematic approach. So yeah, so it comes down to making sure that they're all at the same pressure.
Yeah.
And on trees, that's hard, right? Because the tree spacing is really far apart and you have 1 micro sprayer per tree. So then we end up breaking it up and we'll go over a couple tree rows. We'll do like maybe 4 on this tree row, 4 on the next tree row, trying to make sure they're all at the same pressures.
Listen, a fabulous presentation today. I want to thank you so much for doing it. It was so interesting, and you some of the information I'd seen before but never explained in such an easy way to understand. So awesome. Thank you. I know all our viewers really appreciate that. I hope you'll come back in the next few months and kind of get into some of these more details, because I think,
yeah, absolutely.
I think we'd use it.
And then it's just one more time, I'll do a little sales pitch here. ITRC.org, right, is our website there. So
we're going to
get the book or the evaluation software or maybe register for that class, yeah, go ahead and check that out, itrc.org.
Tell you what, we're going to send everybody a thank you this afternoon for attending, and we'll put
Super.
that in the we'll put it in the thank you. And
hey, Ryan,
yeah.
long time no see.
So hopefully we'll get a lot of hits from that. A lot of thank yous right now hitting our chat. So and thank you to all of you who spent your lunch hour with us again. Gave us your time, which we really appreciate. And wow, I think you got fabulous information today. Thank you again, everybody. Have a great weekend. Hope you enjoy it. Stay safe out there, and we'll see you next week. And remember, all our trainings are on the Janes USA website, so you can go back and always review them there, especially when there's a lot of good information. It's always great to review. They're on podcasts too. We're on Spotify, Google Podcasts, and Apple Podcasts. So check us out when you're driving around farm to farm. Okay, thanks very much, everybody. We will see you next time.